Hello everyone, this is Professor Brian Macon. I am your derivative dealer, your integral interpreter, your calculus confidant, coming to you live. Well, I guess technically I'm not live, you're watching a recording, right? But you get the point. Alright, so we're here to talk about another technique of integration. We're going to look at what we call trigonometric substitution. Now, again, we could be very rigorous mathematically. We could spend 2 hours discussing derivations and development with rigorous math. And I just really want to focus on some technique, and then I want to look at some applications, some word problems. Because remember, the beauty of mathematics is how we apply it in our real-world scenario. Some applications to engineering or other aspects of science. So anyway, let's first of all look at the technique of integration that we're going to call trigonometric substitution. And I need to switch to my pen mode. Right? So we're going to look at trigonometric substitution. All right, now in this conversation, usually what we focus on are integrals that have radicals. Right? So if I have a square root, cube root, things of that nature, where u sub doesn't work, u substitution doesn't work, typically that's where we will utilize trigonometric substitution. So I just want to start off with a quick example here. And let's look at the integral of, let's say, x over the square root of 4 minus x squared. I want to point out to you that in this example, we could do u substitution. So let's say we do u substitution here, because if I can do u substitution, that is a much more straightforward approach. Right? So remember, first of all, u substitution works wonderfully when I have a composition. So I have a composition here of a root and then a quadratic underneath. Now, if u sub is going to work, the composition, right, the inside of the composition is what we're going to let the substitution be. And in order for this to work, I need the derivative of this term to appear in some form outside of the composition. So in this example, you can see x times dx is the du term, basically, right? So I'm gonna highlight this in red just to illustrate. Right, here's x dx right here. So if I solve for x dx, I'm going to get negative 1/2 du. I don't know why this keeps changing size, so I will stop fighting it. So the x dx is a negative 1/2 du. So this whole term, x dx, I'm going to replace with negative 1/2 du. And then I'm going to have the square root of u in my denominator. So in terms of this integral having a radical, it turns out that the u substitution is actually a little simpler of a way to deal with this. So let's go ahead and complete this problem, and then we're going to come back and redo this integral using our new technique of trig sub to see that we get the same answer here. Right, now obviously to complete this integral, I'm going to go ahead then and pull the integral out, the constant out of the integral. And then I have, this is 1 over u to the 1/2, which I'm going to write as u to the negative 1/2, right? So again, remember, properties of exponents, if I pull it to the numerator, changes the sign of the exponent. So then I'm going to use the power rule here, which says I'm going to add 1 to the power, and I'm going to divide by that new power. Right? So there's my antiderivative. And I'm going to flip and multiply this, so I get negative 1/2, I get 2u to the 1/2. So the 2's cancel, and I get negative. And then remember, the 1/2 exponent is really the square root, and my u was the 4 minus x squared that we had above. Right, let me scroll back up for a second. Remember, our u was the 4 minus x squared that we had here, and so we really have the square root of u. And there's our final answer, negative the square root of u, and I'm going to go ahead and box that in, and let's say here is our final answer. Oops, I'm forgetting my plus c on my last line. All right, so we could do u sub for this problem, and in any scenario where I'm not instructed to use a particular technique, of course I want to use a technique that is simplest. So I would do u sub for this problem. However, let's come back and get the same exact answer here using trig substitution. So let me put a little line here and say we're going to use trig substitution. Now, here's how I like to discuss trig substitution. The concept here is we're going to use trig functions to substitute for expressions in the integral. So in other words, if I come back and look at my original integral, here's pretty much the approach that we want to utilize for trig sub. Right? That's a square there. Right? So we're basically going to draw a triangle. So I'm going to come over here. I'm going to draw a triangle. I'm going to call that angle theta. And what I want to do is really replace, I want to attack the radical. So one way we could label our triangle here is, let me switch colors. Let me switch to blue. So if I put the radical term on this side, in order to satisfy Pythagorean's theorem, I would have to put the x here and the 2 here. And we could quickly, I'll go through the work of the satisfying Pythagorean's theorem just to show you this is true, but I don't want to dwell on this here. Right? So real quick, let's just show that we would be able to satisfy Pythagorean's theorem here, right? So if I do, let's say a squared plus b squared equals c squared. So let's say, here's a, I'd have the square root, 4 minus x squared squared. And then let's say, this is the other leg, and that has to equal the hypotenuse squared. So we can see pretty quickly the way that we labeled this triangle, we're going to have 4 minus x squared plus x squared has to equal 4, and those cancel, and we get 4 equals 4. So in this section, when we set up a triangle to use trig sub to solve these integrals, we're going to want to make sure that our triangle is set up so that we satisfy Pythagorean's theorem. And we'll have a strategy we'll talk about in a couple minutes where we will write down kind of a shortcut of what those labelings should look like. And so just to move forward here, now that we know we have set up the triangle so that it satisfies Pythagorean's theorem. And again, when we talk about strategies in just a moment, we're going to talk about, what I kind of already mentioned, right? We're attacking the radical term. So we're going to place the radical term, on the triangle, and then attack the integral from that form. So here's how I like to approach this. So notice that I have a dx term. So just like in u substitution, right? Let me scroll back up for a second. Just like in u substitution, when I let u equal an expression, I have to find the du term. And the du term allows me to replace the dx. So we replaced this dx term using the derivative of u. So that same concept here, we have a dx expression, and we're going to take the derivative to replace that. So in other words, if I look at this triangle, sine of theta is opposite over hypotenuse. So I know that sine of theta is x over 2. And that allows me to say that, x is 2 sine theta. So I'm going to think of, x as a function of theta. So if I take the derivative of x as a function of theta, the derivative of sine is cosine. So if I multiply the d theta over to the other side, we have an expression for dx. So this dx expression, 2 cosine theta, is going to replace this dx expression here in just a moment. Now also, I have an x in my integral, and from my triangle, we said that x was 2 sine theta. So in just a moment, we're going to replace, right? We're going to substitute with a trig function. So again, there's the name of the section. We called this trig substitution as a technique of integration, and that's because we're replacing expressions with trig functions. So the dx gets replaced with a trig function, the x gets replaced with a trig function. And then last but not least, we need to replace the radical So when I come over here to my triangle, I'm going to notice that cosine of theta is adjacent over hypotenuse, and that's going to allow me to find the radical expression. So let me scroll down here and write what we just said. Cosine of theta, let me see if I can zoom out here a little bit, right? So we said cosine of theta is going to give me the radical over 2. Right? So cosine of theta is the radical over 2. So spilling onto the next page. So I have the radical of 4 minus x squared over 2. And all I really want in my integral is the radical term. So I'm going to take this equation we just wrote, and I'm going to point out that 2 times cosine of theta is that radical term. So now I have a trig expression to replace every x expression in my original integral. The x we're going to replace with 2 sine theta. The dx we're going to replace with 2 cosine theta d theta. And then the radical in the denominator we're going to replace with 2 cosine theta as well. So let me come over here. This integral I'm going to write down here with all the substitutions. So the x in the numerator we said was 2 sine theta. The radical in the denominator we said was 2 cosine theta. And then the dx term we said was 2 cosine theta d theta. So there's my converted form of the integral. Now I apologize for bad board management here, right? Let me take this integral down here. And you can see, let's say these 2's cancel. Looks like these cosines will cancel. So I have a 2 left over, which I'll pull outside the integral. And I have a sine theta d theta left over. So here's the cleaned up version of my integral. And we know that the integral of sine is negative cosine. So there is our antiderivative. We took the antiderivative of our original integral. Well, it's not really the original integral, it's the substituted version of the original integral. So because we have this new variable, we need to go back to the x variable. So what I'm going to do here, I'm just going to rewrite this one more time. I got to go back up to my triangle and I have to say, well, what is the cosine of theta? Well, if I go back to my triangle, I can see that the cosine of theta is adjacent over hypotenuse. So cosine of theta is the radical over 2. To be honest with you, I didn't really need to go back to my triangle to do that because I had already written that down right here. Right? But the cosine of theta is the radical over 2. So let's replace that. So we have negative 2 times. So we said the cosine of theta was the radical over 2 plus c. And we can see these 2's will cancel. Right? So we end up with negative the radical of 4 minus x squared plus c. And there is our final version of our antiderivative in terms of the original variable x. And you'll notice that is the exact same answer we got from doing u substitution. Now, again, if I can do u substitution, I'm going to do u substitution. But all of the problems you would typically see in a textbook within this conversation of trig sub, u sub isn't an option. So we have to do trig substitution. So let's do this. Let's take a look at a strategy, right? So how do I set up my triangle? And then let's look at another example or two. All right, you guys, so I just wanted to pause the video real quick so you didn't have to watch me write all of this stuff down. Of course, feel free to pause the video on your end and write this stuff down. But here's the basic strategy, right? So if I have a, let me put a couple little squigglies between here, right? If I have a radical that's like a number minus x squared, just like the example that we just did, this would be how I'd want to set up my triangle. And what that would necessitate is that x is a sine function. So again, like we saw in our example, sine of theta would be x over a, so x equals a sine theta. Now, if I have a radical that's x squared minus a number, I'm going to put that on the other leg, right, the opposite leg of theta. And what that's going to do, if you notice, cosine of theta is a over x, or secant of theta is x over a. And there's my x expression. And then the last strategy being if I have a plus sign under the radical. So if I have a plus sign under the radical, I'm going to put the plus sign on the hypotenuse, and then I'm going to put the x on the opposite side, the a on the adjacent side. I forgot my theta here. So that the tangent of theta is x over a, or x equals a tangent theta. Now, a couple things I just want to mention here about these strategies in particular, right? One reason that the strategies, well, the main reason the strategies are set up this way is so that, first of all, the triangles satisfy Pythagorean's theorem. And secondly, if we look at these two triangles here, we really could have put in the radical on any of the legs, not the hypotenuse. So I could reverse these two on opposite legs and it would still work. However, this would change. This would be a cosine instead of a sine if I were to do that, right? And then if I reverse these on opposite legs, right, I would end up with really a cosecant here, right? And then if I reverse these two legs, I would end up with a cotangent here. Now, none of that would be incorrect, but here's what would happen, right? If x was a cosine instead, the dx expression would be derivative of cosine is negative sine. So my dx would have a negative in it, which is nothing wrong with that, right? But the typical strategy is, well, we might accidentally drop that negative or make a minor error in our work. And so we just want to avoid the negative sign if we can, but it wouldn't be incorrect. Again, if I reverse these two, this would become a cosecant. The derivative of cosecant is negative cosecant cotangent. Again, we're introducing a negative in the dx term, just causes possible errors down the road. And then if I interchange these two, this gives me a cotangent. And then again, derivative of cotangent is negative cosecant squared, and I'm introducing a negative sign. So you could still set them up in, reversing the legs, and the integrals will still work out. We just introduce a negative when we do that. Nothing wrong with that, but this is going to be kind of the better strategy. Now, one other thing I want to just discuss strategy-wise, and then we'll look at an example and we'll see that in action, is usually when we're replacing an expression in the integral, we want to involve, the variable and the side with a constant. So, for example, if we look back in our prior example, let me scroll up here. If we look back in our prior example, when we were wanting to replace the let me zoom out here for a second, right? When we were wanting to replace the x expression that was right here, we involved the side with x and the side that was constant, because it's really easy to move a constant on either side of an equal sign. And if you look down here, right, we had sine theta being x over 2, and it was easy for us to multiply both sides by 2 to solve for x, if you will. And then ditto when we were trying to replace the radical. So what we did is we involved the side with the radical and the side with the constant. Again, because it's really easy to move a constant on either side of an equal sign. So we took cosine of theta being the radical over 2. That was what we wrote down here. And then we just multiplied the 2 to the other side and we had the radical. So within my strategy, when I'm looking at my triangle and I'm saying, I need to replace this or I need to replace that, I'm going to always pick the this or that and the constant side. And that's going to make my life really simple in terms of how we simplify these radicals. So now that we've discussed the setup here, let's take a look at another example. All right, so let's take a look at this example. In this example, we're going to look at 1 over the square root of, let's say, x squared minus 5. So if you take a look at this real quick, I can't do u substitution. If I tried to do u substitution, I would want to let u be the inside of the composition. If I let u be this quadratic, x squared minus 5, the derivative of x squared is 2x, and I don't have an x times dx waiting for me to replace that du term, right? So I know u sub doesn't work. So I'm going to do trig sub, right? That's our conversation. So that's the approach we're going to take here. So again, usually at the end of a conversation where you look at the 4 techniques of integration in, let's say, a Calculus 2 course, you talk about strategy. So you might be given an integral and you're not told the technique to use. So 99% of the time when I have a radical, it's a trig sub problem. unless use substitution works, right? But it would be a trig sub problem. So let's go ahead then and set up our triangle here. And let me switch colors just to distinguish a little bit. So I'm going to go ahead and set up my triangle. So my strategy said that when I have x squared minus 5, when I have the variable minus a number, I'm going to put that on the opposite side of my angle theta. So the number that's being squared, I put the square root of that number on the other leg, and then I have the variable here. So if we look back up at our strategy, that would be the setup. Right? So again, if I have x squared minus a squared, here's a, and here's x. So let's go ahead then and replace terms. Excuse me. So remember, back up in the strategy, we talked about if we set the triangle up accordingly, properly, as we talked about in our strategy, that the x would be a secant theta. So we had x equaling the a times secant of theta. And again, just to point out to you where that comes from, cosine of theta is root 5 over x, right? Adjacent over hypotenuse, or secant is hypotenuse over adjacent. So when I'm involving the x and the side with the constant, it makes it really easy to solve for the x. Now, if you notice, I don't really have an x here like we did in that prior problem. What I'm going to go ahead and do then is take the derivative of the x expression. And the derivative of secant is secant times tangent. This is bad board management. There's a d theta here, right, that I'll plug in over here. So I'm going to have 1 over, and so my dx is going to be secant theta tangent theta. Well, let me erase this and give myself a little more room. Right? So I'm going to have the dx gets replaced with root 5 secant theta tangent theta d theta. Right? Okay. Now the radical I need to replace in the denominator. So let's find the radical. Now again, remember, what I'm going to do here is involve the side that has the radical and the constant. So if I look at this theta, the radical is opposite, the constant is adjacent, so that's the tangent function. So I'm going to go ahead and say tangent of theta is the radical over, right, opposite over adjacent. And again, the advantage to using the radical term, which I'm trying to get rid of, and the side with the constant is I can just multiply the constant to the other side, and I have root 5 tangent theta equaling the radical. Okay. So in the denominator, I'm going to replace the radical with root 5 tangent theta. All right, so we are done with the replacement. We're done with the substitution. We've substituted all the terms in our x integral here, and we've replaced everything with functions of theta, trig functions of an angle theta. Now let's go ahead then and clean this up a little bit. We can see that the root 5s would cancel here, and we can in fact see that the tangents would cancel. So what we end up with is the integral of secant of theta d theta. So there's the cleaned up version of our integral, and then now we take its antiderivative. So at this point, usually in a calculus textbook, the integral of secant is a known result. So we shouldn't have to do any other technique of integration other than to know that the integral of secant is the ln of secant plus tangent. Right, so we're jumping to a known result there. And again, just like in our prior example, I don't want my antiderivative, right? We evaluated our integral. We're done with our integral. We don't want our antiderivative to be in terms of the substituted variable theta. We want it to be in terms of the original integral. So I got to scroll here, but what I want to look for is what's the secant and what's the tangent off of that triangle. Right? Now, I really don't have to scroll too far because I know what the secant is. Right? The secant is x over root 5, and I know what the tangent is. The tangent is the root over root 5. So let me go ahead then and plug those in. The secant was x over root 5, and the tangent was the radical over root 5. So I have the ln of all of that plus a constant, right? And so we're done. So there's our antiderivative in terms of the original variable x. So there's trig sub. There's a second example of trig sub. Now I just want to extend this example for a moment, because if you look up this answer, in the back of a book, or you use some website to find the antiderivative for you, or even some calculators can find antiderivative symbolically. This won't exactly be the answer symbolically. So here's what we're going to do in this scenario, just to make the connection to what you might see in software. So I'm going to go ahead, these have a common denominator, and combine them. And then there's a property of logarithms. There's a property of logarithms that said if I have the ln of, let's say a over b, that's the ln of a minus the ln of b. So in regards to a property of logarithms, we might have seen in an algebra course, I can write this as the ln of the numerator minus the ln of the denominator. And then kind of the last step to make the connection to what we might see on a calculator or software is all of this right here is really just one big constant. So I could think of c minus ln root 5 as just some other constant plus d, right, or plus c1, or whatever we want to call that, right? So what you would see in the back of the book, or in a piece of software, or in a calculator, would be this guy. And of course, they don't use the letter D, they use the letter C, but there's just one big constant there, right? Now, depending on the instructor that you have, this version up here might be acceptable, right? Or they might want you to clean it up, or if you're matching some piece of software to see what that looks like. All right, so let's do one more example. We're getting to about 30 minutes on the video here, and I don't want this to get too long. But this is always a really fun example for me that I like to do in my classes. So what I want to do in this example is, let's say that we want to derive the formula for the area of a circle using trigonometric substitution. So we're going to use an integral, right? So back in a Calc 1 course, one of the applications of integrals is that you look at an integral is calculating an area. Now, one of the prior videos, we used integrals to also find volumes of rotation, areas between curves. You can even use integrals to find work, and within a physics context. There's other applications of integrals that we'll look at in some future videos, but one of them being area. So let's suppose we have a problem that says, prove the area of a circle with radius r is a equals pi times r squared. So let's suppose here's the scenario I want to look at, right? And visually, here's how we would set this up, right? So keep in mind that probably the simplest way to draw our circle to make our work as easy as possible is I'm going to look at the circle centered at the origin. So if I look at this circle centered at the origin, where I have, a radius of r, right, in that case like minus r, and then here's minus r. So there's my circle centered at the origin, radius of r. Right? So the equation we learned in an algebra class is that x squared plus y squared equals r squared. Right? Now, a couple different ways to attack this, right? But the way that I'm going to attack it is I'm going to find the area of the upper half of the circle, and I'm going to double that. Right? And the reason I'm going to do that is when I find the equation for the upper half of this circle, that's going to simply be solving for y. So just algebraically, if I solve for y, I got the square root of r squared minus x squared. And again, algebraically, right, in an algebra class, technically there's a plus or minus here. The positive root gives me the upper half of the circle. The negative root gives me the lower half of the circle. I'm only going to deal with the upper half. Right? So when I set up the integral, so the area of my circle is going to be really twice the integral under the curve. r squared minus x squared. Now my limits of integration in this case are minus r to r. So this integral that we've just set up is going to give me the area. If I cover up the 2, the integral that we just set up is going to give me the area under the upper half of the circle, and then we're going to double that to get the area of the true circle. Now, based on my strategies, when I have a integral has a radical, when I have a squared minus x squared, the way that we set that up is we put the a squared minus x squared on the bottom leg, and then we had the x on the other leg and the a on the hypotenuse. And oops, my quote-unquote number I have in this case is r. Alright, so again we had, sine of theta was x over r, or x was r sine theta. So my dx is r cosine theta, d theta. So I'm going to replace the dx that we have here with r cosine theta. Running out of board space here as I typically do. So before we do that substitution, we want to replace the radical as well. So when I look at the triangle, I want to involve the radical and the side with the constant. Right? So I want to involve the adjacent side and the hypotenuse. So that's cosine of theta is the radical over r. So I'm going to write cosine of theta is the radical over r. Right? So the radical is r cosine theta. Right? So when I replace, I'm going to have r cosine theta. I'm going to have r cosine theta. So when I do that replacement, I'm going to have twice the integral of r squared cosine squared of theta when I do that work. Now I'm going to get a little lazy here, and I'm not going to plug in my limits of integration, and here's why. Right? I don't want to say that the limits of integration are minus r to r, because remember the minus r to r are the x limits of integration. Right? So I don't want to plug in minus r to r for theta limits of integration. That would be incorrect. So I'm going to leave the limits of integration off. Let's go ahead and find the antiderivative, and then we'll go back to the original x variable, and we'll go back to the x limits of integration. It's a way that I want to attack this for a particular reason. You'll see why in a moment. Right? So I'm going to pull the r squared out, and then I have the integral of cosine squared. So in a prior section, we talked about evaluating integrals of trig powers, and the strategy to deal with a cosine to an even power, where I had no odd powers, was to write cosine squared as 1/2 plus 1/2 cosine of 2 theta. So we used what we call the half angle identity, which is kind of odd because it's a double angle. Right? Usually when you look in a trig textbook, they call this half angle because what they write is cosine squared of half theta, and this is a 1 theta. Right? But this is the version we're going to use in this case. So then we have the integral of half is 1/2 theta. Oops, I'm forgetting my 2r squared. And then the integral of cosine 2 theta. Right? The integral of cosine 2 theta is 1/2 sine of 2 theta. So, technically here's my antiderivative. So I'm done, and I want to replace to get back in terms of the original variable. Now before we do that, two things I want to point out to you here. Right? So first of all, how do I find theta? So if I go back to my triangle for a second, let's scroll back up here. I want to find the value of theta. So a couple different ways to do this. Excuse me. I could take this expression right here, the cosine, and I could solve for theta, and I would have theta equals the inverse cosine of that expression. Now that's kind of ugly and involves a radical. I don't really want to use that version. So what I'm going to do is use this version here. So if I solve for sine, that's x over r, or theta is inverse sine of x over r. Right? So again, from our triangle, we had that x over r was sine theta. Right? So inverse sine of x over r is theta. So that's what we're going to use to replace this expression here. Now the other issue that we encounter here is that we have sine of 2 theta in this expression. We only have sine of single theta from our triangle. It is not correct to say that the sine of 2 theta is twice this side. That is not correct, right? So what we're going to do is use an identity. We're going to point out the double angle identity. Sine of 2 theta is 2 sine theta cosine theta. And the reason we use that identity is because my triangle, I have sine of single theta, and on my triangle, I have cosine of single theta. So our antiderivative that we have here, I'm going to replace theta that's here with inverse sine of x over r. So I have 2r squared, and I have the 1/2. You know what? Why don't I just go ahead and distribute that 2r squared. This is going to get annoying to carry that through. So 2r squared times here, the 2's cancel, and I get r squared. I have inverse sine of x over r. And then I'll distribute the 2 here. The 2 in this half cancel, and I'm still left with one of those halves. So I get r squared over 2. So the sine of 2 theta we're replacing with 2 sine theta cosine theta. So these 2's cancel, and then I'm going to replace sine and cosine with their expressions off the triangle. So finally I have this guy, inverse sine of x over r, plus the 2's cancel, I get r squared. So sine of theta was x over r, and then cosine of theta was the radical over r. Right? So if I scroll back up to that triangle, we see those expressions. So we have our antiderivative in terms of theta. We convert that antiderivative and back to the original variable of x. So now that we're back to the original variable of x, we can evaluate from minus r to r. Now we'll plug in those values, and we will get the area of the circle. Right? So if I plug r in, the top limit, I'm going to have r squared inverse sine of, so when I plug r in for the x expression, I get r over r, which is 1. And then if I take r here and plug it into this value, notice I'm going to get r squared minus r squared, which is 0. Here I'm going to get r over r, which is 1. But I'm going to have 1 times 0, and that's 0. So I'm just going to say plus 0 there. So I do upper limit and then minus lower limit. So when I do lower limit, right, I'm going to take negative r and plug into my expression. So when I plug negative r into here, I'm going to get negative r over r, which is negative 1. So I get r squared inverse sine of negative 1. And then same as we saw 30 seconds ago, right? When I plug negative r into this expression, I'm again going to get r squared minus r squared, which is 0. So negative r over r is negative 1 times 0, which is all a big 0. So we have r squared times inverse sine of 1. So what is the inverse sine of 1? Right? So this says, what do I take the sine of to get 1? So I take the sine of pi over 2 to get 1. So I have r squared times pi over 2 from inverse sine of 1. And then I'm going to subtract, and then I have r squared. So what do I take the sine of to get negative 1? So I take the sine of negative pi over 2 so that I get 1, right? So sine of negative pi over 2 is negative 1. So there's our evaluation of the two inverse sines. And as you can see in this case, right, negative of a negative is a positive. So I get r squared pi over 2 from this first expression here. And then minus a minus is a plus. I get r squared pi over 2 there. When I add those together, get r squared pi plus r squared pi all over 2 with a common denominator. You can see that I have 2 of the same expression in the numerator. R squared pi plus r squared pi is 2 r squared pi's. And then the 2's cancel, and there's our pi r squared, which is the area of a circle. Isn't that cool? I love that problem. All right. So on that last example, we were deriving the area of a circle using an integral from a Calc 1 course. an integral can be used to find an area under a curve. And in this case, we found the area under a circle, and that proves the formula is pi r squared. All right, so this video is already getting long enough. That wraps up an example of using trigonometric substitution for evaluating integrals with radicals.